And we're rolling.
Okay, thank you. Okay, welcome to problem solving session 2. We'll be going over signals first, shift and scale. Something that we did last time, but I'll be talking about in more detail and at a slower speed now. Then we'll talk about signal energy and power and how to calculate it in MATLAB. Okay. Then we'll talk about type of signals and then systems, type of systems. Okay, so that's the plan for today. Just stop me and ask me any questions that you have at any point of time. Okay, so let's start. First, I'll be going over laptop. Okay. So first is the unit step. All of us know what unit step is defined as. Let me define it for you once. So unit step, u of t, okay, u of t is equals to 0 for t less than 0 and 1 for t greater than 0. At t equal to 0, u of t can be either 1 or 0.5. Anyone remembers when it is 1 and when it is 0.5 in MATLAB? Which functions? There were two functions in MATLAB that we saw last time. Okay, so the two functions are Heaviside and step fun. So step fun defines u of t at t equal to 0 as 1, and Heaviside defines u of t as 0.5 at t equal to 0. Okay? Are we done? So this will look like this. The unit step looks like this. U of t, and this is t, your time axis, this is the origin. Okay? So when, let's see what shift does. So when u of t is, let's say, u of t plus 2, okay? So now this will be centered at t plus 2 equal to 0, that is t equals to minus 2. Okay? So So this will be shifted to t is equals to minus 2. Okay? So this is an advance in time. The signal has advanced in time by 2 units. Okay? Now, if we do a delay, that is u of t minus 2. Oops, sorry. This is centered at t equal to 2 now. So your signal will be like this, t equal to 2. So the step comes at t equal to 0 in normal position. When it's advanced, it's now coming at t equal to minus 2. It's coming 2 units before the standard time. And when it's t minus 2, it's coming at t equal to 2. So you've delayed the signal. So a right shift is a delay, a left shift is an advance in time. Okay? So let's just see this in MATLAB. Okay, MATLAB standard definitions that I had done last time. First is clear all, close all, and CLC. Clear all clears all the variables that you have defined in your workspace at that point of time. Close all closes all the figures and the plots that you have opened up. And CLC clears your command window. So if I have anything typed out in my command windows, like a is equals to 2, so CLC will clear the command window only. It's not clearing the variable. A is equals to 2 is still there, if you can see. Okay? Now clear all will clear all these variables in your workspace. So now you don't have any variables. Okay? So it deletes everything. Okay. Now first, this is a normal script that you define in MATLAB. You can run your script either by pressing F5 or this run button that you want. So I run it and I get my plots. So first let's see what have I done. For the unit step, I've just defined my x or t time axis from minus 100 to 100 with an increment of 1. Okay, so it starts from minus 100, increments by 1 every time, and ends at 100. Okay, then step 1 is my unit step function. Okay, it's centered at 0. So first argument is x, which is your time axis values. second argument is where it is supposed to be centered. Okay, so you can shift it from here directly. Then figure and plotting as I had shown last time. Okay, now here I am writing a shift of 20 units. Okay, so let's see how it will look. This is from the first step. This is my standard unit step. I'm getting my step at t equals to 0. Okay, next I shift it and now my step is at t equals to 20. Okay, so this is just a normal shift that you can see in MATLAB, what we've just seen in theory. Okay, and you can make changes to plus 20, minus 20, whatever you want. So if you change this to minus 20, let's see, oops, sorry. Now my unit step was centered at t equal to 0. Now it's centered at t equals to minus 20. Okay. Now you can see a new command over here which is called pause. So pause, as it's evident from the word, it pauses the execution of your script at that step, unless and until you press some key on the keyboard. Okay, any key on the keyboard. Then it goes to the next step. Okay. So this was shift in the unit step function. Now the rectangular pulse. Just to define the rectangular pulse for you. Our rectangular pulse is defined as this. So it's going from minus t to t. This is your time axis. This is rect of t, as you can call, and it's centered at 0. Okay, so the width over here is 2t. Width is 2t. Okay, you can change this width. Now, our rect pulse can also be defined as a difference of two unit step functions. Okay, so let's see how you can define that. This first edge that you can see here, you can look at it as a unit step function. So this is like a unit step function centered at minus t. Okay, then this is a second unit step function which is centered at t. Okay, so you have a second unit step function centered at t. You subtract the second one from the first one, and that's it. So u of t plus t minus u of t minus t. Okay, make sense? Okay, any doubts on this? Anything at all? Okay, so let's come back to MATLAB. In MATLAB you can define your rectangular function using the rect pulse command. Okay, so let me just run this for you. Okay, so what we are doing here, as usual, our t is getting defined from some range, minus 5 to 5 over here. Rect pulse is the function that creates a rectangular pulse for us. T is your time axis values, W is the width that you can change. By default it's 1, so you can change it to 2, 3, 4, whatever you want. Okay, then it's normal plotting. So plot, first you have your x-axis and then you have your y-axis. So x-axis are your time values and y-axis are your rect values. Okay, and a shift in this as well. So this is the one centered at 0, the rectangular pulse. Okay, next it is now shifted by, it is advanced by 1 now, so it's now centered at minus 1. Okay, so you can shift your rectangular pulses also in time. Okay, next we'll go over triangular pulses, scaling it and reversing a function in time. So whatever these operations I'm telling you about, shifting, scaling and reversing, you can do it with any function. These are just examples of a triangle pulse or something else. You can do this with some other functions also, like sine or cosine as well. Okay, now let's run the triangular pulse thing. Oh, sorry. Okay, so first going over the code that we have. Again, my time axis is defined. Oh, sorry, I went up. My time axis was defined earlier only. Now tripulse is the function that gives me triangular pulses. Here the width Second argument is the width. Again, by default the width is 1 over here, but you can change it. Okay, everyone understands what I mean by width. Let me show it to you. So this point till this point, that's your triangular pulse width. That's the thing that I mean as width over here. Third argument is your skew factor. So if your triangle is symmetrical or asymmetrical, then it's simple plotting. So this is our standard triangle pulse right now, centered at 0, but skewed because I've applied a skew factor of 0.5. Okay. Now I'm just going to reverse it. No, first I'm scaling it. First I'm scaling and then I'm reversing it. Okay. So the blue plot that you can see, that's my standard pulse. The red one is scaled by a factor of 2, and the yellow one is scaled by a factor of half. So when you say, let me write it down for you. So let's say xt is some function. So scaling can be two ways. Either it can be xa of t or xt over a. Okay. Here let's say a is greater than 1. Okay. Right. So when it's xa of t, you are shrinking your function. It shrinks or compresses. And when it's xt over a, then you are expanding your function. Okay? So if initially your function is of this sort, so this is x of t, xt of xa of t will be like this. Okay, this is xa of t, so it's compressed in time, and xt over a will be like this, so it's expanded over time. Okay, this is what we are showing in MATLAB right now. So let's go back to the plot. The blue one is the standard one that we have, red one is the shrinked version, and yellow one is the expanded version. So let me show it to you. Blue one is this plot, my standard triangular pulse. Okay, red one, which is the shrinked version, is 2t, so it's shrinked by a factor of 2. Okay, and the yellow one is 0.5t, that's t over 2. Okay, so it's expanding. Okay, that's all. Okay, so now time reversal is nothing. I'm just using minus t over here. Instead of t, I'm just using minus t. That reverses it for me. Okay, so this is my original, this is my time reversed. It's mirror image about the center point, which is t equal to 0 over here. Okay, now going over to the next thing, impulse function, which we had seen last time. Impulse function is standard. So let me write it down for you. Impulse function. So del t is centered at 0 and it has area of 1. Okay. Now you can shift this at any point of time. So let's say we'll go to del t minus 5. So the pulse will now be centered at t equal to 5 and the area will still be 1. Okay. So always remember that the area under an impulse is 1. Okay. So whenever you multiply a function with an impulse, so let's say this is my function, some random function x of t. Okay, and I'm multiplying it with an impulse centered at t equal to 2. Okay, this will give me the value of x of t at t equal to 2. Oh, sorry. So this is x at t equal to 2, or let's say x of 2. Okay, because everything apart from impulse is 0 everywhere else apart from t equal to 2. When it's multiplied, it will only give you the value of x function at that instance in time. Okay? So coming back to MATLAB, so this is the impulse function centered at 0. This you can shift in any direction by any amounts. Okay? Now coming to complex exponential signal. So complex exponential signal has a standard format. Complex exponential. So our function, let's say f, is equals to e raised to power s of t. Okay. Now s is a complex number over here. And this can be scaled, so you can have a factor of k also over here. It's a random amplitude that you can choose. Okay, anything that you want, 2, 3, 4. So s can be 0, s can be real, and s can be complex. Okay? Or only real, or s can be only imaginary. Okay? So let's go through what will happen. So this is the function that we have, ek into e raised to power st. What will happen when s is equals to 0? We'll get 1. So we'll just get k, right? So it will be a constant function. So f is a constant function. Okay? When s is real, then what will happen? Let's say s is equals to 2. So, and let's assume that k is equals to 1. So our f will be e raised to power 2t, and this will be a standard exponential function. Okay? If s is negative over here, so if s is minus 2 only, so this will be a decaying exponential. Okay? Now, if s is only imaginary, like let's say 2j, okay, then f is equals to e raised to power 2jt. That means what does that mean? What is the expansion of e raised to power 2jt? Euler's identity. That's it. Cos of 2t plus j sine of 2t. Here we are only plotting your real part of the function, okay? So you'll have a cosine function. Oops, sorry, cosine will go like this. Okay, so cos of 2t. Now, when s is has both real and complex parts, then f will be e raised to power 2 plus 2jt. So that is e raised to power 2t. All good? So this will be a complex function multiplied by this expansion. So it will go like this. It will expand in time. So this will expand in time. Okay? That's the whole meaning of complex exponentials over here. Okay? So let's see it. Okay. Now, my time again is here from -2 to 2. You can define any values. First thing I've done, s is a constant, s is 0, k is some value 2, and let me run it for you. So I'll get a constant function. Okay? Next, when s is real value, either +3 or -3 over here. So s is equals to this sigma, +3, or you have -3 over here. Okay? So you'll get your exponentials. Blue is your expanding exponential, that is a positive power, and red is your negative power. Okay? Next, and exp is your MATLAB function for exponential definition, just a reminder. Now next is you have only an imaginary part to it, so your exp is e raised to power j omega t, and omega over here is 5, so you'll get a standard cosine centered at 0. So this is ranging from -2 to 2, and your cosine is going like this. Okay. Next we'll have a proper complex exponential which has both real and imaginary. So this is raised to a negative power, so it's decaying with time. Okay, your cosine is decaying with time, right? That is that. Now when you do shift and scale operations on complex exponentials, so you can apply a shift and scale together. So by together I mean you have a function g of t, shift and scale, so it's like g of 2t plus 1, g of minus t plus 3, etc., etc. Okay, it's scaling and shifting at the same time. All right. Now coming back, a nice way to define functions in MATLAB is either using the inline command, okay, or you can define them as, one second, using this format, the variable name and then the function's expression. Okay, so let's go in this in detail. The function that I'm trying to define is e raised to power minus t into cos 2 pi t. This t greater than equal to 0 is just defining a unit step for me. Okay, it's just defining a unit step. All right. Now first I have the function expression and then the variable name, that is t over here. Then you specify the t values and then you just directly plot it. So you're plotting 2t plus 1 over here, not t. Okay, so let's go and see what this looks like. Okay, let me see. This is f, this is, okay. So my normal t was like this. This was my normal t. So in one period, let's say from -2 to 2, I had one oscillation. Okay, but then it's shifted and scaled. Okay, so now within one unit of time period, like -0.5 to 0.5, I have two oscillations now. Right, so it's compressing. Earlier within 1 unit of time I had one oscillation and now I have two oscillations. Okay, and it's also shifted by 1. Okay, right. Another thing that we can do is reverse and shift. Okay, so it's the same function and you're plotting a different format of it. You're reversing and shifting it. So this is the reverse and shifted version. Make sense? First you reverse it and then shift it. Okay. Next, let's talk about the energy and power of a signal. So coming back. Energy and power of signal. So whenever we have a signal, any signal, let's say, any finite signal, okay, this is time and this is my x of t. I can define its energy. Now energy, I cannot take it directly as the amplitude because this area will cancel out the area of this effect of this area because it's negative amplitude over here. Okay, that's why we take the energy as the square. So x of t square dt. Okay, so here x of t is complex. So when your function is complex, first you take its absolute value and then you square it. If it's not complex, then you just directly take the square of it. Okay? Now, all of the signals that we have are not finite in time. Like a cosine is periodic and it could go on till any amount of time. So when your signal is periodic, then we can define a time average. Okay? So power is nothing but time average of your energy. Okay? So power, T is my time period of my periodic signal. Okay? This goes from minus T by 2 to T by 2 and your xt square dt. Okay? So let's say if your signal is like this. Okay? And this is your time period T. Okay? So you're defining the power in this period. So you're only integrating in this period. Okay? So whenever you have periodic signal, just make sure that you're only integrating in the time period of that signal. Okay? Now coming back to MATLAB. Yeah.
So you said in the time period, but
Yeah.
shouldn't you start like the negative period instead of 0?
Oh, I mean here in this case it does not matter.
Oh.
Yeah. Okay. But generally what you do is you're dividing. So here when you divide this period, it's ranging from 0 to t. But if let's say you have a pulse which goes on like this, it's periodic. Okay, and let's say this is the time period for it. Okay, so now you are integrating from, this is minus t by 2. Okay, this is t by 2, and let's say this is some number t by 4. Okay, so now you'll integrate from minus t by 2 to t by 2. Yeah, yeah. Okay. Just remember that you're integrating over one period of it. The limits don't matter that much. Okay, now coming back to MATLAB. Okay, energy. Now, our function, we are again defining a function using inline. So my function is e raised to power minus t right now. Okay, and it's only defined between 0 and 1. Okay, makes sense? Okay. Now, my t is ranging from 0 to 1 because my function is only defined between 0 and 1. I don't need any other t values. Now, how can I define the energy? I can take integrals is essentially summations of values. You're just adding things up. So this is a discrete sort of an implementation where you're taking x, this is a square of xt, agreed? Xt multiplied by itself is square. Don't forget that we're using a dot star multiplication, that is element wise multiplication, because xt are of same size. You can't use a direct matrix multiplication over here. It will give you an error because the inner dimensions won't agree. Okay, so use the element wise multiplication. And then when you're multiplying with a scalar, you're just directly multiplying it. So what this 0.01 means, this is your delta t. The dt that you have in the integration, that's the delta t over here. Okay, so x squared dt and sum is the equivalent of integral. Okay, makes sense. Now let's see the value of this. So first I get 0.4367. Theoretically I should be getting 0.4323 because I'm getting a different value because it's an approximation. Okay, it's a discrete approximation of a continuous function that we are doing. Okay, So that's why there's a difference in the values, but it's not a major difference if you see it, look at it. Okay. Another thing that we can do is we can use the function quad or integral in MATLAB. Okay, so it computes the actual integral that you do by hand in your course. Okay, so first you supply a function name, then the lower limit of the integral, and then the upper limit of the integral. Okay, right, so the function I've defined over here in a different format. I can, both of these definitions give me the same function, just be sure of it. These are just two different ways of defining the function over here. One is inline. I'm using a different format because inline and quad are commands that MATLAB is going to obsolete in some time. Okay, so you might not have it in future. So the integral is another command that you can use in place of quad, and @t_exp sort of so is another way to define functions. So what you're doing is @t is over here the variable, and then you just give the function expression. Okay. Now, if we see from this result, we are getting the correct result of 0.4323, which is expected. Okay. You can go back and check that these values are correct. Okay. Now, here is another function that I integrated from 0 to 100. So, if you have an integration like 0 to infinity, you can take some high value like 100 or 1000 and then integrate it. Okay? Right. Now comes the question of even and odd functions. So any function that you have can be split into its even and odd parts. So let's say if xt is your given function, its even component will be half of xt plus x of minus t, and its odd component will be half of xt minus x of minus t. Okay, and then xt is just a sum of x even plus x odd. Okay, right, so I'll just show you an example of this in MATLAB. Oh, interesting. Let me just, what is happening to my computer? Yeah, okay, weird stuff. Okay, so h I've defined as e raised to the power minus t, and it's only defined for t greater than or equal to 0. So it's e raised to the power minus t multiplied by a unit step function. Okay. Next, I've defined t from some range of values. Now, my standard plot of this function is the first plot over here. Okay, let me make it bigger for you. So this is continuing. I've just limited it in the view of -2 to 2. This exponential is continuing till infinity, as you might say. Okay, so it's 0 for everything t less than 0, and e raised to the power minus t for everything t greater than 0. Okay. Now the even component is defined as half of ht plus h of minus t. That's how I've computed it. The odd component is half of ht minus h of minus t. Okay, and that I have directly plotted in MATLAB. Okay, so the even component, if you see, it's half the amplitude, and it's going both t less for t less than 0 and t greater than 0. Okay, the odd function is again half in magnitude, and is going again for t less than 0 and t greater than 0. Okay, now if you mentally add these two up again, the odd parts will cancel out each other, and the even odd parts, by meaning that parts less than t equal to 0, the signal part that's t less than equal to 0 will cancel out each other, and the parts which are t greater than equal to 0 will add up. So you'll have your original signal back. Okay? Make sense? Alright, so that's even and odd functions. Now coming back to just a few more things that I wanted to go over. One important thing that when you're doing in your homeworks, especially when you're calculating energy and power, is if you have a signal, let's say x of t, you can do shift or scaling operation on it. Okay? Oops, I'm so sorry. Okay. The question is, what effect does this operation have on our energy of the signal? Okay, so let's say if this is our signal. Okay, calculating its energy is pretty simple. You just go from 0 to 1, 2 squared dt. Okay, your 4 will come out of the integral, constant will remain inside. Okay, now you'll have t and you'll just put in the limits. So your energy is 4. Alright. Now, if you shift this in time, let's say now it's from 1 to 2, it's still 2. Your integration limits change from 1 to 2, it's still 2 square dt, and again your constant integrates to t, and again you have 4. So as a rule, as a thumb rule, the time shift operation does not affect the energy of your signal. Okay, so time shift does not affect the energy of the signal. All right. Whereas if you are scaling your signal, so let's say again a same example. So this has an energy of 4. Now if I scale it in time, so this is 2, and now let's say it's going from 0 to half. Okay, so the integral is now 0 to half, 2 square dt, and my energy is now 2. So whenever I scale my function by t, my energy is scaled, so Ex dash, you can say, is Ex over t, is scaled by a factor of t. Okay, so here I'm scaling by a factor of 2, so t is equals to 2 here, my scaling. That's why it's compressing in time. Okay, and the energy is decreasing by half. Alright, so the scaling operation will affect the energy of your signal, whereas the shift operation will not. Okay, so just be careful about this when you're doing your homework questions. Another thing is, if you want to calculate the energy of a cosine signal, let's say cos omega naught t. So this signal is ranging in time and it's going on. Okay, now sorry, not energy, you'll calculate the power of this signal. Okay, because the energy is infinite. Alright, so power, how will you calculate the power? You'll go from, let's say, minus time period of cosine is 2 pi, the period of it, period is 2 pi, you're going from minus pi to pi, for example, or yeah, minus pi to pi is fine, cos omega naught t dt. And let's say this is scaled with some constant. Okay, so this squared. Okay, now you have c square outside, and you have cos square omega naught t dt. Okay, now how will you write cos square? As trigonometric identity. Yeah. You're almost there. So it's 1 plus cosine 2 omega naught t over 2. So cos square theta is equals to 1 plus cos 2 theta over 2. Okay? So this thing becomes integral minus pi to pi c square 1 over 2 dt plus c square minus pi to pi cos 2 omega naught t dt over 2. Okay. Now this integral within the time period is equals to 0, right? Because see, if this is your time period, so this area will cancel this area. I have not drawn it to scale, but your positive area will cancel the negative area. Oh, I'm so sorry. Okay? Right? So your cosine or sine will integrate to 0 within its time period. Okay? So your integration comes out to be c square by 2 into 2 pi. Okay. Now there is a term that I have left over here. Anyone knows which term I have left in my power formula?
1 over t.
Correct. So 1 over t. Okay? Don't forget that. Otherwise, you get this 2 pi factor in your numerator. So this is 1 over t multiplied, and t is 2 pi over here. So your power is c square by 2. Okay? So don't forget the 1 over t factor. Okay? All right. So going through over the signals that we have in general. In general, we get confused with analog, continuous, digital, discrete. Okay? So let's going over those types. So we have analog, there's continuous, there's digital, and there's discrete. Okay? All 4 of these have their own meaning. Okay? Continuous and discrete are with respect to your time axis. Okay? Analog and digital are with respect to your amplitude or the function value. Okay? So let me tell you what I mean by it. Let's say if we have a function, some random function. Okay? This is my x. Let's say it's x, function x. This is my time axis. So right now, my time axis is continuous or discrete? Continuous, right? So it's continuous. And my amplitude axis is? So this is my amplitude axis. Analog, that's right. So what does analog mean? Analog means your amplitude can take any value in the real number space. Okay? Whereas in digital, it can only take a specific set of values. It's not only 0 and 1. Okay? It can take only a specific set of values. okay, like 1, 2, 3, 4, whatever values you define it to be, okay. So this is your analog continuous signal, okay. Let's look at analog discrete. So my analog discrete will have values like this. Some random values on the amplitude scale, any of the real numbers, but at discrete instances of time, okay, not at all instances of time, okay. Now digital continuous is same, it's not, so you'll have digital values, so you have a set of values. So in my amplitude scale, I can take only values from a set, okay, whereas my time is continuous, okay. Now I'll have digital discrete as well. That's again a set of values over here, but discrete in time domain, okay. So that's what different types of signals mean. Going through the systems perspective, two important conditions that we need to test in this course are linearity and time invariance. So for linearity, two conditions need to be satisfied, okay. One is homogeneity and the other is the additive property, okay. So homogeneity means whenever I scale my input with some factor k, my output is also scaled. Additivity means if I'm supplying the combination of two inputs, I'll get the combination of their respective outputs, okay. Both of these can be combined into which is called the superposition property. I'm so sorry. Okay, so this is superposition. So first, the quick test for linearity is if you put an input of 0, do you get an output of 0? If that is not satisfied, your system is non-linear, okay. But if that condition is satisfied, you still need to go further and test these conditions. That is not a fully sufficient test, okay. Now, time invariance. If I'm supplying x of t, I get an output of y of t, okay. What time invariance says is if I shift my input with some factor capital T, my output also shifts, okay, right? Okay, makes sense? So that's it for this session. I'll be here for the office hours if you have any doubts regarding the homework that we have, okay. Thank you, Dan.